Hello and welcome to Lecture 2 in the Energy Unit of Phys 1104. We've met kinetic energy, now it's time to meet a whole other class of energy called internal energy. I'm going to start this lecture with what might seem like a series of strange questions. So here we go. Has this cart just been in a collision with another cart? Think about that. Well, if you think that's too hard, how about this one? Has this cart just been in a collision with another cart? And in case you're not feeling very much like Sherlock Holmes, I'll point out that it's stuck to that other cart with Velcro. How about this? Has this car just been in a collision with something? Well, I think clearly it has. So here's the point. This first cart might have been in an elastic collision, right? Say, using the magnets. But we can't tell, because that collision has left this cart unchanged. Now, I'll tell you, in fact, I know that just before this picture, this cart had been in a collision with another cart, but there's no way of telling from the picture. On the other hand, this other cart and the car have definitely been in collisions, and those collisions were definitely totally inelastic, because they're still stuck to the things they collided with. Well, how about this one? This car's definitely been in a collision. Think about it. Was that collision elastic? Do you think it bounced off with the same relative speed after the collision that it had before? There's a pattern to be seen here. All of these objects, the two cars and the cart that stuck to the other cart, have been changed in some way by the collision they were in. In the case of the cart, it's sort of a subtle change, right? The hairs on its Velcro have been rearranged and perhaps bent and meshed with the hairs of the Velcro on the other cart, but it's still been changed. On the other hand, this cart hasn't been noticeably changed at all by the collision it was in. Well, look, all of the ones where the object was changed were inelastic collisions, and the one where the object wasn't changed was an elastic collision. To talk about this, we'll say that these inelastic collisions have changed the state of one or both objects in the collision. What do I mean by state? Well, it's the configuration of the system, as you could describe by every single physical variable that could be measured for the object. So it includes everything: the shape of the object, its temperature, its chemical composition, its phase, right? Is it solid, liquid, or gas? Anything you can measure is part of the state of the physical object. Any transformation of a system or an object from one state to another is called a process. We need to distinguish between two very different types of processes. So some processes are what we call reversible, and that means that they can undo themselves spontaneously. By spontaneously, I mean without us interfering. So for example, here's a pendulum swinging back and forth. And it can undo itself, right? You can think of the swing to the right as the process, and it undoes itself as the pendulum swings back to the left. The other thing to notice is that if I were to play the video of the swing to the left backwards, you'd be unable to distinguish that from a video of the pendulum swinging to the right. Well, let's try that with a different reversible process. Here is an elastic collision between two carts, and here it is played in reverse. Or maybe I just lied to you. Maybe I played you the reverse one first and the forward one second. Look back at them and see if you can tell which is which. The point is, you really can't, and this is showing us that elastic collisions are reversible processes. There's no permanent change in the system state, and so it looks the same at the end of the process as it did at the beginning if the process reverses itself, which an elastic collision does. But some processes are irreversible. For example, here are some fried eggs. These will not spontaneously uncook themselves, unscramble themselves, jump up out of the frying pan back into the shell, seal the shell shut, and get back into the carton. So these processes do not undo themselves. This car has been in a very irreversible process. It will not uncrash and be a perfectly fine car again. And For an irreversible process, the forward process looks different from its reverse. So you can tell very clearly that this video of these cars crashing is in reverse. Inelastic collisions, then, are clearly irreversible processes. This idea of understanding whether a process is reversible or not is going to be crucial to us as we go on. So let's check that you're understanding it. So let's think about two processes. One is a mass hanging on the end of a spring, and it moves down, which stretches the spring. The other process is a stone falling, and it hits the ground and comes to rest, and as it hits the ground, it leaves a dent. So, which of these processes are reversible?